Hello, welcome to this presentation of our paper dealing with atypical instances in evidential decision making. This is a joint work with Marie-Hélène Masson and Sébastien Destercke. So this presentation will be divided into 4 points. After a short introduction, I'll present some background knowledge. Then I'll speak about conformity management and cautious decision making, and I'll end up with a small conclusion. Okay. The topic addressed here is that of supervised classification. So basically, we have a set of training instances associated with class indicators. And we want to build a classifier that is a model which generalizes, which makes it possible to classify any new test instance into a class. Okay, so basically, we can do this by transferring the training information with respect to the classes to any new test instance. For instance, to the right, we can see that the new test instance, the black cross, falls into the region of a blue class, and we will classify it into the blue class. So this requires to assume that the training data are similar, the test data are similar to the training data. And as a matter of fact, there might be various sources of uncertainty in the data. The training data may be scarce, may be uncertain, or may be irrelevant in order to classify new test data. And this is this latter point, the irrelevance of the training data, which we will consider in this work. Okay, let's talk about the various kinds of uncertainty which we can encounter in cautious classification. So basically, we may mention ambiguity when a test instance falls between two classes. We may also mention the lack of data. In some regions of a space, we do not have many training data, and we cannot classify with a high certainty a new test instance. And basically, these two kinds of uncertainty can be handled by using appropriate frameworks and models for representing ambiguity, for instance, or lack of data. Here we will consider nonconformity to the training data. That is, we have training data and we could get many training data, but they are not relevant in order to classify the new test instance. Here we can see that the test instance falls into a region where we do not have any training data. We want to distinguish this case from the lack of training data because it's not exactly the same. We could increase the size of a training set as much as we want, but we would not be able to classify any better the test instance. And we propose to handle nonconformity by propagating the conformity information, for instance, by weakening the classifier outputs, and then use an associated decision strategy. Here, we will not address conformity quantification. This is a problem which might be related, for instance, to density estimation or novelty detection. And we will not address here because it is a whole topic in itself. We will assume that instances come with a conformity degree. We will concentrate on conformity management and cautious decision making. So we want to consider classifiers which are cradle, which provide mass functions as outputs. And more precisely, they will use the imprecise Dirichlet model in order to model epistemic uncertainty. And we also have this conformity degree, which we will propagate through the model using a specific conformity operator. And in the end, we want to do some cautious decision making by using a specific strategy which will depend on the conformity operator that we have proposed. Okay, so belief functions in a nutshell. We will consider here classifiers which provide mass functions as output. So we have a variable of interest. Here, this is the class of a new test instance to be classified. And the mass function quantifies what is known about the class of a test instance. So M of A for any subset of classes A is the probability of only knowing that the instance belongs to one of the classes in A. The mass given to omega quantifies therefore complete ignorance with respect to the actual class of an instance. and the mass given to the empty set can be interpreted as the belief that the instance belongs to another class, which is not known yet. We can define belief and plausibility functions from the mass function. The belief degree is a degree of support to a subset of classes, and the plausibility degree is a degree of potential support to this subset of classes. We can use these degrees in order to compare classes. For instance, if a belief given to some class is greater than the plausibility given to another class, then we can say that this other class is dominated by the former. There are a number of operations on mass functions. We may cite combination, conditioning, marginalization, and discounting, which makes it possible to weaken the information contained in the mass function by transferring a part of the belief to omega, to full uncertainty. When it comes to decision-making, various strategies may be employed. There are some crisp decision-making strategies, for instance, pick the class with maximal plausibility. And there are also some cautious approaches, such as interval dominance. So we can compute the set of non-dominated classes where the dominance relation is that presented in the previous slide. Okay, we will consider here classifiers with cautious outputs, and we will use for this purpose the imprecise Dirichlet model. So assume that we have a local classifier, such as a decision tree, which provides class counts. We could use the class frequencies in order to compute probability estimates for the classes. But here we will introduce a new parameter, S, which is basically a number of virtual instances with unknown class information. And it will make us possible to define mass degrees according to the class counts and this parameter S. Okay, so in the example to the right, we can see that S is equal to 2, and we define mass degrees, which are not directly the class counts, but also take into account this parameter S, which quantifies somehow a number of instances with unknown class information. So the greater S, the larger the uncertainty, the smaller S, the smaller the uncertainty. We can see that if we compute the belief and plausibility degrees from the mass obtained via the imprecise Dirichlet model, so the belief plausibility intervals are wider when S is large. And in this case, we can see that we have a high uncertainty due to the lack of knowledge. If we use, for instance, the interval dominance decision strategy, if S is sufficiently large, then the belief degree for any class will always be smaller than the plausibility degree for any other class. And that means that no class will be dominated by the others. And using the interval dominance strategy in this case will basically lead to retrieve all classes as a prediction. Okay, how do we propose to handle conformity? Basically, we propose to define conformity operators in order to propagate the conformity information through the mass function. And this will result in a revised mass function, which we can use then in order to make a decision. And we will apply a decision rule to a revised mass function according to the conformity degree. And of course, the choice of both the conformity operator and the decision strategy should be made jointly according to some desired properties. We can mention a few of these properties. Class preference preservation. So if we increase or decrease the conformity degree of a test instance, it will not alter the dominance relations between the classes. Decision strengthening means that if we decrease the conformity of an instance, we will narrow down the set of possible classes. And decision weakening, the reverse, means that if we decrease the conformity of an instance, we will expand the set of possible classes for this instance. Our first proposal consists in taking the mass function provided by the classifier and discounting it according to the degree of non-conformity. The limit case is that if the conformity is equal to 0, if the instance is completely non-conform, then we will have a vacuous mass function after taking into account the degree of conformity. Okay, and we can see that then the belief degree will be 0, the plausibility degree will be 1 for each class, and we will thus model complete ignorance. If we use interval dominance as associated decision strategy, then as a limit case, we can see that when the instance is completely non-conform, we'll retrieve the complete set of classes as final decision. And this proposal satisfies decision weakening. In this example, we can see that if the instance is completely conform, we retrieve here two classes, since class green is dominated by class blue. If we decrease the degree of conformity, then we will actually integrate class green into the final decision. Our second proposal consists in adding an unknown class to the set of possible classes. And formally, it means that we extend the initial mass onto a new frame, which is the original frame plus this unknown class. Then we will transfer the mass to this unknown class proportionally to the atypicity level. Okay, and as a limit case, we will transfer all the mass to the unknown class. If we use interval dominance in conjunction with this conformity operator, then we can see that at some point, the unknown class will become supported. And we can see that the unknown class is supported only if the others are not. Okay, and it means that we can define a variant of this decision strategy. We will use interval dominance on all classes except the unknown class. And then we will add the unknown class to the set of predicted classes whenever the belief degree for some class is less than the non-conformity degree. Okay, and in case of complete atypicity, then if we use the decision strategy, which we call interval dominance with atypicity trigger, it means that for completely non-conform instances, we will get the unknown class as only prediction. In this example, we can see that for a completely conform instance, we have the same prediction as before with the interval dominance strategy. If we decrease the conformity of the instance, then we can see that with interval dominance, we will predict either class blue or class red or an unknown class. And if we further decrease the conformity degree, we can see that with the interval dominance strategy, in the end, we only predict the unknown class. Rather, if we use the atypicity trigger decision strategy, we will predict class blue or class red or class unknown because we have left out class unknown when we applied interval dominance. Our third proposal consists in adding an unknown class to the set of possible classes, as before. That is, we extend the mass function onto this new augmented frame. But after that, we discount this extended mass proportionally to the level of atypicity. And as a limit case, then what we get is a mass function which directs all the mass to the set of possible classes plus the unknown class. And after that, we can use the interval dominance decision strategy. In case of complete atypicity, basically, we will end up with a prediction which is the set of possible classes or the unknown class. Okay, so in this case, we can see that if we have a completely conform instance, we will predict class blue or red. And once we decrease the conformity degree enough, we will here end up with the set of all possible classes. And if we further decrease the conformity of the instance, we will end up with a set of possible classes plus the unknown class. Okay, let's go to the conclusion. We have presented here a work in which we want to handle non-conformity in a classification setting. So basically, we might have test instances which differ from the training data. It is a kind of epistemic uncertainty, but it cannot be addressed by collecting more training information. And we want to handle this non-conformity in a belief theoretic setting. So basically, we define a conformity operator, which makes it possible to propagate a mass function, conformity degree through the mass function, by revising the mass function according to the conformity level. And we will define jointly conformity operators and a decision rule, an associated decision rule. So we might have several properties. Class preference preservation, basically conformity does not alter the relations, the preference relations between the classes, and decision strengthening or weakening, which makes it possible to restrict or augment the set of possible classes according to non-conformity. So basically, the contributions are that we formalize the desired properties of conformity and decision strategy, and we can guide the choice of a strategy according to the setting. For instance, in novelty detection, we are in an open world setting. We consider that there may exist classes which we do not know yet, whereas in anomaly detection, this open world assumption is arguable. We rather want to see whether the instance is a new one or not, an atypical one or not, and we do not care about identifying new classes. Future work might include defining some additional properties for conformity operators, and of course, new decision strategies. And basically, we want to compare our approach to approaches dealing with atypical instances, such as in conformal prediction. And of course, for this purpose, we will need to do some extensive experimental evaluation. Thank you for your attention. If you have any questions, I'd be happy to answer them.